do this. Hello everyone, it's October 26th. All right, so we redid this one this morning, added a bunch of optimization, including the idea of impacting or not impacting from yesterday. Yesterday night, I was thinking about that. So we have the impacting or not impacting, so we don't have to do the recheck like every single node, so I can return it immediately. So that's one speed up, and another speed up is we are not using hash map at all. So absolutely no hash map. We use completely the array, because array is much faster than hash map, and then we just have to set it to the maximum length. So wow, awesome, Jimbo. And yeah, with these two measures, and then we got a pass, right? We pass it, but with very poor performance, right? Only 5%. So definitely we didn't hit the right solution, but it worked. Okay, it worked. That's very important. So for this one, I think what we can do, I mean, I haven't read the solution yet, but there are some hints. So we can go through the hints and kind of see if there is some other inspiration we can get from this. So yeah, that's that. And I guess we will just continue with today first. Okay, count square submatrices. Let's see what this is about. Count square submatrices with all ones. Given n by n matrix of ones and zeros, return how many square submatrices have all ones. So in this one, we have 15, 10 with 1, 4 with side is 2, and 1 with side is 3. It has to be squared, so it's either side of 1, side of 2, side of 3. Gotcha. This is side of 1. 1, 2, 3, 4, 5, 6. Side of 2, you have 1. Okay. Interesting question. So, how do you plan this? I mean, we have only 300 by 300. I wonder, we definitely need to go. Well, I have an idea, because the count is the number of ones is either 1, 4, 9, right? It's square, right? It's square. So we just need to know, because I am approaching this with two-dimensional prefix, 2D prefix sum. You know, that's kind of my thinking at the moment. We just need to find how many is ones, how many is 4, and how many is 9. Okay, let's see how we can do this. So let me give myself an example for the first one. 1, 2, 3, right? So 2D prefix sum for matrices, if I remember right, each one is a sum of everything, right? So that's gonna be 0. How do we do this? 0, 1, 2, 3, and we'll do this and we add up. So this is gonna be 1, so it'll be 2, so it'll be 3, 4 will be 6, 7 will be 10. That is not right. Dude, what are you doing? This is absolutely not right. Let me redo this. It's 1 plus 2, 2 plus 1 is 3, that's right. And then 3, this is 5. Right, 4, this is 7. And this is going to be 1. This is 1 plus 3 is 4. Yes, it is 4. So because it's the whole thing. And this is a 1, this is 2, 7, 3 is 10. Okay, that is the entire thing. So for each ending, we can compute by itself, right? we can do a size 1, size 2. Yes, we can say size 1, size 2, because we know the length, right? So we know the maximum it can be. So we just don't go there. So as you go through every single one, so that's OMN, and then you will go through the sides, 1, 2, 3, 4. So, ooh, we're looking at. I wonder if there's a better way. Well, we can check because we have this sum. This is like everything, right? So we can do this and this. Okay, that's actually not bad idea. Not too bad idea. So when we see 1, so we need to know if how do you compute this? So you do your sum minus this sum minus this sum and a plus this, right? So 5 or minus 2 minus 3 plus 1. That'll be whatever is here. So that's size 1, right? And then we can say, let's try size 2. Try size 2. This we don't have anything, so we just say remove this part, right? Because if we want to add this, yeah, we can handle. So we say remove this part. So it'll be 5 removes 1 will be 4. That is, so we have 4. And then we'll do 3. We need 9, but this doesn't have 9, so we don't do it, right? So in this one we have 2. I think this will work, right? And this again we do 1. Minus plus, we're good. Now we do 2, so we minus this thing is 4, which is good, right? I wonder. Don't wonder. I don't think can do it the other way. And then we cannot do other. And this we can do. Actually, no, it's 4, right? If we do 2, we're gonna remove this one. So we're gonna remove 1. That's 3, so it doesn't work, right? 7. We can do this. We get 1, and then we get 4. Oh, okay. I can see this will work. A 2D prefix sum. Is everyone at every, and then you just check if it's possible, right? Just check if it's possible. Okay, we'll give it a shot. Well, technically it will run OMN times, because you have to go through every cell, right? And times the side, M or N, the smaller of the two. It's technically, I think that's the runtime, but we'll see how this one goes. Ooh, forgot we got one more. All right, I have to do some analysis here. Okay. Alright, so what do we have? So we'll do matrix, right? And then we have this. We need to first do, let's just do it in place. Okay? Yeah, let's just do it in place. And int p sum, right? We'll do 0 for n matrix dot length. M, no, that's M, that's N, and matrix 0 dot length. Okay. Let's get a p sum inside. Okay. All right. So first one, we just say p sum plus equal to matrix ij, right? Okay. And then we'll add something above. Then we say if I is larger than 0, right? Then we do matrix ij shall equal to p sum plus I is larger than 0. If I larger than 0, then matrix I minus 1 j, otherwise 0. Right, so we update that, and then we keep going every time we add, and then if it's larger than 0, then otherwise, and once we're done, we reset p sum, right? We reset p sum is 0, and then we'll do it again. Okay, so this will make our prefix, right? And then we will go through them one more time, and now we have a count. All right, so for each one, I have the value, right? And I have the current, so we say int side. We say start side equal to 1. Okay, now we just say while side times side is smaller or equal to matrix I and j. Okay, if it's smaller, then we have a possibility. Right, now we're gonna try. What do we try? We will do this, and then we will yes. So we say int minus top. Right, minus top will be I. And 1, you just minus 1. So I minus side. Right. If I minus side is larger than 0, because 1, if I want 2, right? Then minus 1 minus 2, right? That's, yeah, so if I minus 2 is larger or equal to 0, if it is, then minus top is in the matrix I minus side j, otherwise 0. Minus top minus left, it will be j minus side, right? If it's larger than 0, if it is, we say matrix I and j minus side, otherwise 0. Okay, and then we say if matrix ij, and int plus top left diag, that shall equal to I minus side larger equal to 0. Yeah, because it's gonna be here and it's gonna be here, and j minus side larger equal to 0. If that's true, then matrix I minus side j minus side, otherwise 0. Okay, so this is going to be minus top. Let's just call top, right? Left diag. So we're going to say minus top minus left plus diag. If this is equal to side times side, then rest plus plus, and then side plus plus. And false, right? So you're either equal or you're not equal. I think the first time that you're not equal, then you can just, because if you cannot support, like say a 2 by 2, you will not be able to support even higher. So else, just break. If you can support the cut like a 1 by 1, yeah, we try 2 by 2. If you can support 2 by 2, we try 3 by 3, right? But if you cannot support even 2 by 2, what's the point of trying 3 by 3? You're not going to be able to support. So we do that. And yeah, every single one will do it. Matrix ij. And at the end, I think we just return res. Okay, so this is my solution. I'll say it's very straightforward. 1277. Use 2D prefix sum to find for each cell. Then at each cell, check if a square can be formed with the cell be in the bottom right corner. OMN to do the first, and then the last one, technically you should multiply, I think, by the minimum of M and N. That's what I think. So you have to go through the side. And technically, if you have something that's full of, let's first run these two test cases just to see if this method works. Yeah, it works for this, but now the really interesting part is if you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I don't know, just keep going, right? So that's that. Actually, we do this. To see how much time it will take. Oh, okay, it doesn't take that long. Okay, let's just submit it. Maybe we'll get a pass. Yeah, well, not the fastest, but no, we get a pass. Now, once we complete this, we can start thinking about if there's any optimization that we can do. I mean, optimization. Yeah, this is more or less a brute force kind of way. Optimization, we can say if we hit something that it's full, then we don't have to go through this. That is an optimization, right? If it's full, completely filled, then we know how many. Exactly. If it's completely filled, then we know how many. I know I know J. So we do that, right? Okay, so one optimization that we can do can be like this. Right, it's the first optimization that I can think of. We can implement some speed up. For example, if matrix ij, if the prefix sum at matrix ij is equal to, right, is equal to I times j. Actually, no, it's I plus 1 times j plus 1, right? If that is the case, then every cell is filled. All the cells are filled, right? All the cells are ones. In this case, the number of squares is minimum I plus 1, j plus 1. Right, so we don't have to. So this shall save us a lot of time. if the matrix is not sparse. Right? If the matrix is not sparse, this shall save us a lot of time. And maybe we can even I am thinking. Let's just give it a shot. Like we say ij, right? And then we say if matrix ij, okay, so equal to I plus 1 times j plus 1. Okay. In this case, rest plus equal to, because I can always do the minimum, mass.minimum, I plus 1, j plus 1, and I continue. Okay, let's see. Maybe this one will speed things up. Even if just a little bit, I think it will help. That is wrong. It's recite. Try it again. Yep, let's see if it makes any difference. Not really. It's interesting. Okay, so that does not work. That does not make it any faster. Okie dokie. Anything else that you can think of? Anything else that you can think of? Maybe what we can think of is I mean, technically we don't have to go two times, right? We can do it in one run. But really, you think that's gonna make any difference? Honestly, I don't think so. I don't think so. I think, I mean, what you're trying to say is we can put this part right inside here, because we update the matrix, and then we put inside here, and we put this one here, and then we delete this one pass. Everything else is the same. I don't think this is gonna make any difference. Yep, you're just getting slower and slower every time you run it. No, that's not it. So you still haven't found the key. Let me think. I don't know. Like, just any hint? Oh, yeah, it's just the same. Well, do you have a better way to DP? There's some DP thing here. Wait, what? Oh, row times column. It's a DP. Really? How is this DP? So I would say if it's DP, then let's say at ij, I know how many there are ending up at ij. Okay, and then I have I plus 1, j plus 1. Hold on, let me see. How many ending up with this? 0. How many ending up this? 1. How many ending up? Yeah, this is also, if it's a 1, that's a 1. And this is a 1. Okay. Here, 1 and 0. Alright, so this one. How many ending up here? Well, the number ending up here, what I need to know is how many ending up here. Like if I have, dude, if so basically we're looking at this, right? If I have, let's say, x and y, I have a y, this one has y, this one has x. If it's 1 just by itself, then you cannot extend. If it's 2, that means you can extend here. And if it's 2, then you have at least 2. Right? If it's 1, then you have nothing because this doesn't have anything. If it's 2, then you have 2. But if this is 1, but if this is 2, then you definitely have 2. Right? So if this one, let's say if I need to have 3, if this one needs to have 3, this must be 2. This must be 2. This must be 2. Right? 2, 2, 2 will make it this one 3. Anyone cannot be 2, 2, 2, then this one doesn't have 3. Right? So we'll say 2, 2, 2 will make this one 3. And if I have 4, if I require 4, if this is a 4, then this must be a 3, this must be a 3, this must be a 3. Ah. So if it's a 1, 1, 1, then I have a 2. Right? So this is if it's a 1, you have a 1. And then you check these 3. So this must be, this only have a 1 because this one is not a 1. Because only 1, 1, 1 give you a 2. 1, 1, 1 is a 2. 1, 1, 2 must be, yeah, 1, 1, that's a 2. Right? Here, that's a 1. There's a 1, 1, 1 give you a 2. 2, 2, 2 give you a 4. I'll give you a 3. So in total, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15. Wow. Yep. That is it. This is it. So did not read the official solution, but got a big hint from it. We shall use dpij is equal to the number of squares ending at matrix ij, right? Ending at matrix ij. Now, for if matrix ij is equal to 0, then dpij equal to 0, right? Otherwise, dpij shall equal to minimum dpi minus 1j dpi j minus 1 and dpi minus 1 j minus 1 plus 1. Because 1, 1, 1 give you 2, 1, 1, 0 give you 1, right? And if we hit the side, that basically just means you don't have it, right? Basically means you just don't have it. Like if you're here, this is a 0, these is 0, this is 0, basically 0, 0, 0. So you get a 1, right? This is the same thing. Yep. Okay, and we are going to do it on, we're going to do it in place. Right, for int I 0, I smaller than I plus plus. Okay. For int j 0, j and j plus plus. Okie dokie. If matrix ij, yeah. And just to be lazy, we will implement the dp matrix on top in place. So if this is equal to 1, right? If it's equal to 1, again, top shall equal to I larger equal to 0, I minus 1 larger equal to 0. Right, if it's true, then it's matrix I minus 1 j, otherwise 0. Left j minus 1 larger equal to 0, and matrix j minus I j minus 1, otherwise 0. Int diag I minus 1 larger equal to 0 and j minus 1 larger equal to 0, and matrix I minus 1 j minus 1, otherwise 0. Alright, and then matrix ij shall equal to math.minimum top left math.minimum diag plus 1. And then rest plus equal to matrix I j. I mean, I don't even need this, right? Matrix dot length, matrix 0 dot length. There we go. Perfect. This is the solution. The fast one. It is. It is. Because this is OMN, and I don't see it can be a how do you make it even faster? Wait, what do you say? Oh. Okay, let's check if it's yes. Yes, we got this one. They do a new one, which is fine. Minimum, list this. If we go to 1. Oh, they create a little bit more, so don't know. You know what? I do believe this might be faster because we don't have to do all these extra checks. Interesting. Let's try this. What if we do not do extra checks? So same as solution 3, but we create an auxiliary, pretty sure I'm spelling wrong, auxiliary DP array, and making it one bigger on both row and column, and this way we can avoid excessive if condition checks. So basically we do dot length 0 dot length, right? And then we say int dp new int n plus 1, right? Then we do this. You good? No. I'll do this first. All right, I'm back. So yeah, we have that. And then we I think we just make this change. Say m+1. Oh, right, and then don't do this. It'll be dp I minus 1 j, right? dp I j minus 1, and then this will be dp I minus 1 j minus 1, and that is dp, and then we will do dp. Okay. Yeah, let's see how much time extra condition checks will cost this whole operation. If this is faster, then we kind of know. So this solution and this solution is exactly the same. There are differences here. We use extra, but we avoided a lot of if checks, and that seems to make it faster. So don't do too much if checks. Yeah, this is the fastest solution. So don't do too much if condition checks. Okay, good.